simplify the Maxwell's relations here by writing to B, it is equal to mu times H, and D is of course epsilon times E. Then we have these two equations and only two unknowns, E and H. Eliminate, for example, H, and we will have an equation for E, and let's solve that. We had the gradient of E. Let's take a second gradient of that. Good point. Curl of E, double curl of E. It means the curl of, what was this, minus j omega mu H. And now, let's remember, mu is constant. The medium was constant. I mean the parameters, it is like a homogeneous, meaning that mu doesn't change in time. It is not a function of time. If it were in a function of time, then this differential operator would operate on that. But since it is not, then only H. Yes?
Maybe function of space.
Oh, yeah, okay. I'm sorry, it is too early morning for me. Gradient, you remember differentiations with space. Thank you, Sami. With space. But now that it came to my mind, then if mu were a function of time also, then in our earlier derivation with t, we would have been forced to take care of that. But now, since this is spatially uniform, it can go, all this can come outside the nabla, because nabla only operates on H, minus j omega mu, curl, thank you, Henry, of H, which is then, what is it? Do you remember? The other Faraday law, Ampere law, sorry, it is j omega epsilon E. Was it so? Let's check. Yes. And now, what is this? J times j minus 1, and there is another minus 1, that gives us omega squared mu epsilon E. Yes. And then, okay, this is a bit complicated. Double curl. You may have heard this, what is it, the back cap rule. Have you heard back cap? It is back cap, B, A, C minus C, A, B, back cap. And now we have to have dot here and like this. You can, it's a bit complicated. Has anybody heard? This is of course, like a memorizing thing. Well, which means that this double curl can be then written as minus then this Laplacian operator of E. Well, this is a bit abstract, I mean the del operator, but let's get rid of that soon. But the fact is now that we have here the divergence of E. And earlier we had, if I go here, so it is 0, which means that del epsilon E is 0. And since epsilon is constant in space, this means that epsilon, like this. Do you agree? Which means that the divergence of E is 0. If epsilon is constant, uniform. Otherwise we cannot take it away from there. But that only means that this is now 0. And we get a simpler relation. Can we get it from here? Here we have double of E. Let's put it to the other side, then probably plus omega squared mu epsilon E equal 0. Helmholtz equation. Okay, and this is valid at every point in the homogeneous region. So now let's have the simple solution, which is so-called plane wave. And plane waves are important in electromagnetics because even if they are very like an abstract and idealized cases, they are very useful in analyzing even practical situations. So plane wave, as its name says, it is like a plane. There is a plane in which the field is like independent, is like independent on the variation. There is no variation. So it means that there is only one direction, say, let's say z direction, where there is variation. So in x and y it is uniform. There is no variation. The fact is that, you know, the nabla squared is the second derivative of x plus second derivative of y plus second derivative of z. Of course, then becomes only second derivative of z. Because if there is no variation in x, the derivatives of x are 0. Similar to y. These vanish. Okay, and then it only means that our field, our Helmholtz equation becomes the second derivative. Let's take a total derivative of z of e, which is a function of z is only z plus omega is always 0. Okay. And now, of course, now this is a vector. But it is also a function of z. So the vector, now it's important. The vector, in fact, is transversal. You know that electromagnetic wave, plane wave in simple medium is transversal, meaning that E is okay. Oh, let's derive that. Let's see where do we have our okay. Let's take our old friends. E is divergenceless, meaning that this is valid, and since Hubble only has the z component, now we get the derivative here. Okay, let's yes, right.
Is there any reason that you changed from the partial differentiation?
Yes, that is a good point. Yes. No, in fact, there is no reason for that. I just am so much more used to having the total differentiation. The fact that it can be done is due to the fact that we only have one variation. There is no like a second order variation through x or y or t here. So, but it mixes up. So let's keep it then as a partial derivative. Yes, thank you for that. Okay, but anyway, then let's assume for the moment we come back to the fact that what is the vector direction of the electric field. You may have heard that light, electromagnetic field, is transverse radiation, meaning that it's propagate that direction. The field is in the transverse plane. It could be polarized this way, or circular polarized, or unpolarized, or whatever. But it doesn't have the longitudinal component in ordinary media. So let's just assume that E is now, say, x-oriented. Doesn't matter